Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to learn how to calculate the activation energy using the Arrhenius equation. What I have right here is an energy profile for an exothermic reaction because the reactants are on top of the products. So if the reactants change into products, energy is going to be released. But some students think that it's just a direct path from the reactants to the products, and that's not the full story. What really takes place is that the reactants have to overcome an obstacle, kind of like this hill, okay? And if we draw a dotted line from the reactants to the top of that hill, this amount of energy is what we call E sub A, and that's called the activation energy. So what needs to happen is if there's like no energy added to the reactants, this chemical reaction cannot form the products. We have to supply enough energy to get to the top of the hill so that everything can fall down to the products. Okay, that has to happen. So our job today is to actually calculate this idea of activation energy, or kind of like the hill or the obstacle that's in the way between the reactants and the products. We do that by using the Arrhenius equation. Now, the Arrhenius equation is our rate constant being equal to some of these variables. Okay, the first variable up here is going to be the capital letter A, and that stands for the frequency factor. And the frequency factor tells us like basically how many active collisions do we have in order to make this chemical reaction takes place. Remember, this has to deal with the collision theory in kinetics, and that is the reactants have to touch each other, okay? They have to touch each other with enough energy and lining up properly, which we call the right orientation. So colliding with enough energy and the right orientation, okay? And some of those things are involved in the frequency factor, which talks about the number of collisions, okay? As far as the energy is concerned, that piece comes from right here. Remember, E sub A stands for the activation energy. And of course, R is going to be our ideal gas constant, okay? But this R is going to be the 8.314 version because that's in joules per mole Kelvin, which means that this temperature cannot be in degrees Celsius. That temperature has to be in the unit Kelvin, okay? So the rate constant is equal to the frequency factor to base E, okay? And that's to the power of negative activation energy over RT. So if our hill is really big and the activation energy is really, really large, remember this is a negative on the exponent. If you have a really, really large activation energy, that would cause K to be a smaller number. So the larger the activation energy, the slower the chemical reaction will take place. And that makes sense. If you had to get over a small hill versus a gigantic hill, it's going to take you longer to get over the big hill. Okay, so I just wanted to show you how activation energy and the rate constant are related to each other. Okay, so our job is to kind of use this equation to calculate the E sub A. And if you look at this, that looks kind of challenging. So we have to do a little bit of math. What we're going to do is we're going to try to get rid of this E, okay, by taking the natural log on both sides, because eventually we want to get this out of being an exponent and as to just like a standard number or variable. Okay, so we're going to take the natural log on both sides. And when we do that, the left-hand side is going to be the natural log of K, and that's going to be equal to the natural log to the other side, which is going to be A to the E to the negative EA over RT. Okay, that's kind of like what it comes down to. Okay, so we're going to distribute this natural log in two places, okay, because these are multiplied by each other. So the natural log of K is going to be equal to the natural log of A, okay, plus natural log of E, that's just equal to 1, okay, and that's going to equal to the exponent, negative EA over RT. So the natural log of E is just 1, and that's what brings this exponent down, okay? Now, what I'm going to do is I'm going to put this on this side and this on this side. I'm just kind of flip-flopping these two. And you'll see where I'm going with this. So this equals negative EA over RT, and then it's plus natural log of A. And then the last piece is I'm just going to separate this fraction a little bit. Okay, so this becomes the natural log of K is equal to negative EA over R times 1 over T. So I just took the EA and the R and I separated it from the T, and that's equal to the natural log of A. And the reason why I have it in this form, because this is slope-intercept form, and we can actually create a graph in order to calculate this activation energy, okay? So really, this is the Y, and this value right here is the slope, okay? This is going to be our X, and the natural log of A is going to be our Y-intercept. So when we're making a graph, okay, what goes on the y-axis is not going to be just the rate constant. It's actually the natural log of the rate constant, okay? And what goes on my x-axis is going to be inverse temperature. Now remember that temperature, that inverse temperature, it has to be in the unit of Kelvin. It won't work with degrees Celsius, okay? Now, if I graph this out, okay, I'm going to get a negative slope because the m is negative, so it's going to look something like this. And the slope is going to be equal to negative EA over R. So if I calculate the slope and I have the rate constant, look, I can then calculate the activation energy. And that's exactly what we're going to do with the data that we have over here, okay? So now this data over here, the temperature is in degrees Celsius, okay? And we said that the temperature has to be in Kelvin and it has to be inverse Kelvin. In addition, I have the rate constant over here, but I actually need that to be as the natural log of the rate constant. So I have to do natural log of K. So I have a little bit of math that I need to do with my data set in order to figure out the activation energy for this particular reaction. Okay, so I'm going to leave this up on the board. I'm going to do some erasing over here. And when it comes down to it, this is the equation that we actually care about a little bit more. So we got there from the Arrhenius equation, but it's this equation that I care a lot more than this one going forward. So let me erase this stuff from the board, and let's go into trying to create a graph where we can calculate the slope so that if we have the slope, we then can calculate the activation energy, which is the whole purpose of this video, is to calculate the activation energy using the Arrhenius equation kind of like rearranged. Okay, so the first thing that I'm going to do is I'm going to get this temperature into Kelvin instead. So I'm going to add 273. And when I do that, I get 700 and 800 respectively, okay? And then if I take the inverse temperature, okay, that's going to come out to be 0.00143 and 0.00125 respectively. And then I'm going to do the natural log of K right here. So natural log of K, so I take the natural log of 1.3, and that comes out to 0.262. I do the natural log of 23, and that comes out to 3.135, okay? Now remember, I did that so that I get this graph, okay? And if I get this graph, the natural log of K is really kind of like my y-axis, and the inverse temperature is really my x-axis, and I'm going to use these points in order to calculate the slope in order to get the activation energy. Okay, now remember, to calculate slope, it's simply the change in y over the change in x, or basically y2 minus y1 divided by x2 minus x1 that you learned in algebra class. Okay, so I'm going to use this as my y2, this is my y1, this is my x2, and this is my x1 in order to calculate the slope, okay? Now, technically, I'm going to try to use all the digits left in my calculator. So there were more than just 0.262 when I took the natural log of 1.3, okay? And same thing when I do inverse temperature. There were other numbers other than 0.00143. So I'm going to leave all of these numbers in my calculator so I can get the most accurate answer. But if I do y2 minus y1, okay, I'm going to get 3.135 minus 0.262 as my change in y, okay? My change in x is going to be 0.00125 minus 0.00143. That's going to be my change in x. And if I do this, but with all of the digits in the calculator, I get this answer of negative 16,090. Okay. Now, as far as the units, whenever we do natural log anything, we kind of tend to make it unitless in chemistry. But for the temperature, inverse temperature, we have inverse temperature down here, but it's in the denominator. So really the units on the slope here is really Kelvin. Okay. Now remember, that slope is equal to the negative activation energy over R. So that negative 16,090, okay, Kelvin, is equal to negative EA over R. And as long as I know what R is equal to, I can do some cross multiplication to figure out what the activation energy is. I can just simply do EA is equal to negative 16,090, okay, and that's going to be in the unit Kelvin, times negative R, okay, and R is equal to 8.314. Okay, so if this is a negative number there, these two negatives are going to cancel each other out, and my activation energy is going to be equal to 133,772. Now the units on the R is joules per mole Kelvin. And you can see that the Kelvin here are going to cancel out. So I'm left with joules per mole. And if I wanted to put that into kilojoules per mole, I would just divide by 1,000. So this could be approximately 134 kilojoules per mole. This is how we calculated the activation energy from the Arrhenius equation. Now that we have the activation energy, we can actually go on and do some other things, okay? And there's two other things that I want to do in this video, okay? The first thing is I want to figure out the frequency factor, which is going to be the A part of the Arrhenius equation. And then I want to figure out, well, what would be the, what would the rate constant be? Like kind of what would this be if we were at 750 Kelvin? So hopefully it's some number in between 1.3 and 23 as our answer, but that's kind of like what we want to be able to figure out in the second part of this video is what is the rate constant at a different temperature than the ones that are listed. And in order to do that, okay, we're just going to use this equation 2 more times. So I'm just going to kind of put in here that we have the slope, okay, remember the slope is equal to, for this problem, negative 16,090. We're going to have to use that number a couple different places, okay? But remember, this is how we calculated the activation energy. I'm just going to put that over here on the side because I'm going to erase it. But this video now has a second part, okay? And that is, how do we use this information to calculate the rate constant, K, at different temperatures? So let me erase all these stray marks, and we'll get into that part, okay? All we're going to do is use this equation a couple more times. So I'm going to write it down. The natural log of K is equal to negative EA over R times inverse temperature plus the natural log of A. So the first thing that we're going to do is try to figure out what the natural log of A is. And all we're going to do is we're going to plug in our numbers that we have right here, okay? So remember, the natural log of K is equal to 0.262. So I'm going to plug that in right here. This part is the slope, and that's why I wrote that down. I didn't want to forget it. The slope is equal to negative 16,090. And we're going to use this line still. The inverse temperature is 0.00143. And we have basically all the numbers now to figure out what the natural log of A is. Okay, so all I did, once again, is I plugged this in for my Y. this in for my x, and I remembered the slope that we calculated in the first part of this video. Okay, so multiplying these two numbers together, we would get something that would look like this. It ends up being negative 22.99 plus the natural log of a. We're going to bring this to the other side, so the natural log of a is equal to 23.252. And if we did that, we can calculate a simply by taking e, right, on both sides, base e. So base e on this side would give me a, and base e to the 23.252, that number is going to end up being equal to 1.25 times 10 to the 10th power. So this is called the frequency factor. This is how many collisions we're having within this chemical reaction. So this is the frequency factor A. Okay. Now really, I did all of this to kind of calculate the natural log of A, because we're just going to use this equation a second time, but now we're going to fill in our temperature here, okay, in order to figure out the rate constant. So once again, I'm going to write down this equation. The natural log of K is equal to negative EA over R. And I'm going to plug in everything I know, but this time I'm going to put this temperature in order to figure out what K is equal to. Now, we know the slope. It's still negative 16,090. And the value that I'm going to put in is 750. But remember, that has to be inverse temperature. So it's 1 over 750. Okay. And we have our natural log of A that we calculated from the previous part as 23.252. And all of this information is going to give me natural log of K. So when I multiply these together and add the 23.252, I find out that the natural log of K is equal to 1.799. And if I want K all by itself, I'm going to do base E to the 1.799. And that comes out to the answer for my K to be equal to 6.04. So I was actually able to calculate the rate constant at a different temperature. And does 6.04 fall in between 1.3 and 23? Like 750 falls in between 700 and 800? Absolutely it does. So I hope you learned a lot in this. Number one was to calculate the activation energy, okay? And we did that by figuring out the slope, okay? But then we use this slope 2 more times, here and here. First to figure out the natural log of A, and then from that we can figure out the frequency factor, or we could take that natural log of A and plug it into our equation, and then we can plug in any temperature to get any type of rate constant. If you found this content helpful, please give it a like and subscribe. And when you leave a comment, it really does push this information to other students that might be interested in learning chemistry.